We are group 3. Our design is the pulse oximeter, which consists of a microcontroller Arduino Nano, a optical module, TIA transimpedance amplifier, and also a bandpass filter. Here is a power supply that powers up the transimpedance amplifier, which needs a positive and negative voltage. And also the power supply powers up the band filter here. The optical module consists of 2 resistors, 320 ohm, 2 LEDs, infrared and red LED, and a photodiode. The 2 LEDs are pulse width modulated from the microcontroller at pins D3 and D4. The output of the photodiode goes into the analog pin of the Arduino, where it then senses and processes the signal.
However, before the signal from the photodiode goes into the Arduino microcontroller, it first has to be turned into a voltage source, since the ADC in the microcontroller can only pick up voltage. So we use a transimpedance amplifier right here that converts the current from the photodiode into a voltage source. And it consists of an LM742 op amp, 2 resistors, a capacitor on the other side, and it is also powered by the dual power supply right here. Next, after the photodiode's current signal is converted to a voltage signal for the ADC, it goes out into the output of the Arduino with this wire right here, and it becomes sampled in order for the, let's see, I guess we can always change it, edit it. Okay. After the voltage source goes into the ADC with this wire, the microcontroller will take a sample, and it'll take it'll convert that sample into a current. It will mathematically turn it into current, where it will then be able to take the ratio of the current from the IR LED to the red LED and able to find the peaks, which will allow us to be able to determine the R value, which is the ratio of the oxygen concentration. And because we're detecting the peaks as well, we'll also be able to the heartbeat. However, the signal from the TI amplifier is pretty noisy. So whenever we get the beats per minute, heartbeats per minute, and the oxygen concentration, it is a little bit noisy and not as accurate. I mean, it's accurate, but there's just some issues with the sampling. As you can see here, where it's jumping through different values and keeps going no finger on the display. So to counteract that, we use a filter, an analog filter, and this is a bandpass filter that Mark made, and it goes from 0.3 hertz to a frequency of 3.6 hertz, and then it outputs that into here. Now, we were having issues hooking it up to the Arduino, so it's not connected in this case. But ideally, it would be connected to filter the voltage signal. Lastly, the enclosure for this whole thing would ideally be inside of this 3D printed box, as you can see here. And it was created by and designed by Ahmed. And the LCD screen would be on top.
So after the signal is read, what should happen after I put my finger in there, and you kind of see how it flickers off and on, BPM will appear on the screen, as you can see now. Right now it's taking the signal and taking averages. You can kind of see the heart popping up where the BPM is at. The R ratio will pop up, and so will the C constant. As soon as there's enough, there it is. As soon as there's enough averages to be taken, it'll take a heartbeat. And it says I'm at 44 beats per minute and 71% oxygen. It's kind of sort of accurate. It's kind of working. We got lucky right now. So this is what it's supposed to be doing. I might be at 85, maybe. But yeah, there you go.